Hello and welcome back to What's Up Physics. I'm Mariah, and today we'll be learning about frames of reference. Frames of reference are the perspective from which you observe and measure an object's motion. An object's motion will look different based on how you are moving in relation to it. For example, a car's motion would look different to you if you were standing still next to it, if you were inside it, or if you were walking in the opposite direction that it is going. We will first go over the two types of reference frames. Inertial frames of reference occur when there is no acceleration acting on the object whose frame of reference is being used. If the object is at rest or moving at a constant speed, it has an inertial frame of reference. Now, if you are at rest in an inertial reference frame, you perceive yourself and the ground as being at rest. And this makes sense because if you're not moving, your surroundings, which are attached to the ground, would not change, and thus the ground would appear to be stationary. In fact, you can see this for yourself by looking at the ground right now, assuming that you're still. Is it moving? No. But things get a little more complicated when you're moving at a constant speed in a frame of reference, because then you perceive yourself as being at rest, and the ground is moving at that same constant speed. And this might not make much sense to you, because you can feel your legs moving and working to keep you moving forward when you walk. But pretend that you were walking on a treadmill. Your legs and the ground are moving at the same speed in opposite directions. And this means that you are not going to go forward or back. So your surroundings will not change and you will not feel like you are moving forward, even though you are clearly walking. So your motion is not necessarily connected to your frame of reference. They actually did this experiment on pigeons, who bobbed their heads back and forth while moving to stabilize their vision. And what they did is they put them on treadmills that went back at the same speed that the pigeons walked forward. And the pigeons did not bob their heads while doing this, which shows that they felt that neither they nor the ground were moving. The reason this is harder for us to wrap our heads around is because we've been trained to realize that the motion of our feet is what's carrying us forward. However, an easier way to understand this concept without having to think about your physical motion is imagining yourself in a car. Let's say that you're in a car that's moving at a constant speed, meaning that you're in an inertial frame of reference. In this case, if you looked out the window, you would see the ground and trees all moving past you. The idea is that you would perceive yourself and the car as being at rest while the ground moved from underneath you, because you're in an inertial reference frame. You cannot feel your motion. However, imagine that you're sitting in that same car, but this time you're not moving at a constant speed. You're accelerating forwards and gaining speed. You would feel as though you're being pushed back into the seat by some force. In other words, you would feel the motion of the car. This is because you are now in a non-inertial reference frame, and these occur when the object whose frame of reference is being used is accelerating. And you can tell that you are moving in a non-inertial frame of reference because of the fictitious forces that are acting opposite your direction of motion. So going back to the car example, while you do feel like you are pushed back into your seat when the car is accelerating, there is no force that causes this to happen, but inertia, which we'll go over in the next unit, makes it seem like that is the case. This applies even when you are carrying out the motion of acceleration. For example, if you are speeding up while running, because you can feel fictitious forces going opposite your direction of motion. But for this course, we will only be dealing with inertial frames of reference. One important thing to note is that the acceleration of an object is the same in all reference frames. Imagine that you are running and speeding up towards the left with an acceleration of -2 meters per second squared, and your sibling is standing still and watching you do this. Both of you would realize that you have that acceleration of -2 meters per second squared. You would know this because of the fictitious forces that are acting on you towards the right, and your sibling would know this because they can see you speeding up at that rate. Okay, so we're going to be going over 3 scenarios, all of which involve the taxi, the helicopter, the ground, and you. And we'll be measuring the velocity based on a different frame of reference for each scenario. First, we'll be doing it from the ground's frame of reference. So we're going to have you here as an observer, and you're standing still on the ground. What is the ground's velocity? Well, looking at the ground as a stationary observer, you would see that it's not moving and it's just at rest. Now let's say that you look at this taxi, which is going to the left, and you measure that the taxi is going at a velocity of -10 meters per second. And then you look at this helicopter, which is going to the right, and you measure, that's about 8 times the length of this, that the velocity of the helicopter is 80 meters per second. Now, this all might seem pretty obvious to you and easy to understand, and this is because we typically measure velocities from the point of view of the ground, or the Earth. But let's see how these values change when we change our frame of reference. Okay, so this time we'll be finding the velocities of these objects from the taxi's frame of reference. So you're on the taxi, or you're in the taxi, I should say, and you are traveling at a velocity of negative 10 meters per second from the ground's frame of reference. And you get out your measuring tools while you're in the taxi, and you find out that the taxi is stationary. But how can the taxi be stationary when the trees and the ground are being left behind you? This is because when you're in the taxi, it feels like the ground is moving from underneath you and taking your surroundings with it. So what is the ground's velocity? Well, rather than you getting displaced 10 meters each second towards the left, it would feel like the ground is getting displaced 10 meters each second to the right. So, the ground's velocity from this frame of reference would be positive 10 meters per second. Now let's find the helicopter's velocity. So, the taxi and the copter are moving away from each other, so the separation distance between the two increases. At time 1, let's say that this separation distance is x, and at time 2, let's say that distance is y. Now, the separation distance between the two would be the same no matter the frame of reference. So from both the ground's point of view and the taxi's point of view, the separation distance at time 1 would be x, and at time 2 it would be y. But from the taxi's perspective, the taxi is at rest. If the copter were going at 80 meters per second, then the separation distance would be different across different reference frames. From the taxi, it would actually look like the copter is going faster. But what is its velocity? We would add the taxi's speed in the ground's reference frame to the copter's velocity to get 90 meters per second. And if you're confused as to why or whether this really works, then let's use an example. So let's say that at time t equals 0, the taxi and the copter are vertically lined up. So that's your copter here, and that's your taxi over here. So the separation distance between the two at time equals 0 is 0. Now, at time t equals 1 second, I'll just say time 1, from the ground's point of view, the taxi moves 10 meters to the left, and the copter moves 80 meters to the right. So now, their separation distance is 90. Now, from the taxi's point of view, at time t equals 1 second, the taxi is at rest, but the copter moves 90 meters to the right. So the separation distance is still 90, and this proves that this method works. Now we'll be finding these objects' velocities based on the copter's frame of reference. So from the ground's point of view, the copter is traveling at a constant velocity of 80 meters per second. As you might have guessed, from the copter's point of view, the copter's velocity would appear to be 0 meters per second. And if this still feels hard to believe, then think about it this way. If you're flying at a constant speed and you close your eyes, you wouldn't be able to tell that you're moving. The clouds flying past you are what clue you into that, but because we typically look at things from the point of view of an outside observer, we've been trained to always think in this point of view, to think that it's us moving forward and not the sky moving behind. Now, if you're not moving, then why are the buildings and trees falling behind you? That's because from this point of view, it looks like the ground is moving in the opposite direction that you're going at a speed of 80 meters per second. So that's a velocity of negative 80 meters per second. Now the taxi is going in the same direction as the ground, but it's moving 10 meters per second faster than the ground is. So it will have a velocity of negative 90 meters per second. Now, there is a tendency to say that, oh, if you're looking at things from the point of view of the taxi or the copter, you're doing it wrong. That's not their actual speed or velocity. But in physics, none of these frames of reference are more right or wrong than the others. It's like using units. It's not wrong to use miles instead of meters, but you have to make sure that your teammates are all using the same units, so that you're all looking at your problem or experiment from the same perspective. Typically, we measure things from Earth's frame of reference, or the ground's frame of reference, but we should be able to convert quantities into their values in other frames of reference, just like how we use meters in physics, but we should be able to convert those meters into miles if needed. Okay, now let's do some example problems, or one to be exact. Example number 1, the one and only. As an airplane taxis on the runway with a speed of 17 meters per second, a flight attendant walks towards the tail of the plane at a speed of 1.22 meters per second. What is the flight attendant's speed relative to the ground? Now, if the flight attendant were just standing on the plane, then from the ground's reference frame, she'd be traveling with a speed of 17 meters per second. But since she's moving at 1.22 meters per second in the opposite direction, each second, the plane carries her 17 meters forward, and she walks 1.22 meters back. By subtracting these numbers, we find that her distance traveled in that 1 second was 15.8 meters, and so her speed is 15.8 meters per second. Thank you for watching this video. Our next lesson will be on motion in 2 dimensions. If you liked this lesson, please consider liking, sharing, and subscribing to our channel. We'll see you next time.